All right, so hello everybody and welcome to the seminar. So it's a pleasure to have Dervan who will tell us about arcs and K-stability. So please go ahead.
Hi. Hi. Great. Thanks for the opportunity. It's actually very nice to be giving an online talk. It reminds me in a kind of positive way of the pandemic, I guess. So what I'll be talking about today is some strengthening of the notion of K-stability, which is very prominent in birational geometry and moduli theory for Fano varieties. But mostly what I'll be talking about is how we should try to understand the more general situation. So K-stability is something that makes sense for an arbitrary polarized variety, a projective variety with an ample line bundle, but we don't know very much about it. And what I'll talk about today is an attempt to try to prove some new results about K-stability for general polarized varieties. Okay, so to just kind of start off with some motivation, some explanation of the things I'll be interested in. So K-stability, whoops, okay, good. Yeah, and yeah, please complain to me if you can't read anything. So K-stability is, I guess, most well known for Fano varieties. So in the Fano case, always over the complex numbers, there we have a basically complete theory in the various different aims that exist around K-stability. So it's been very successful. And that's through two reasons that I'll say a little bit about. So the first, maybe most relevant to this seminar series, is the connections with moduli theory. We like to construct moduli spaces as part of the classification problem in algebraic geometry, as you will all know. And while, I mean, for Calabi-Yaus and canonically polarized varieties, things work quite well, at least assuming restrictions on singularities. You, for example, automatically get separated moduli spaces. In the Fano case, things are more subtle, and you can't just construct moduli of arbitrary Fano varieties. You need to put some kind of restriction. And it turns out by deep theorems of many people, some of whom are actually here, we can construct a nice moduli space of K polystable Fano varieties. So there is even a projective, so in particular separated moduli space of K polystable Fanos. So in particular, if you're interested in the moduli theory of Fano varieties, then you have to incorporate this theory of K-stability, and that's been a big theme of algebraic geometry and birational geometry over the last 10 years. Also, really, actually, the historically original motivation for K-stability was instead through Kähler geometry. So here, the point is that K polystability was proven around 2012. So this is actually equivalent, again, on a Fano variety, to the existence of a Kähler-Einstein metric. So kind of natural Kähler metrics that you might come up with, they exist on a Fano variety precisely when the variety is K polystable. So these are kind of very important just from Kähler geometry, so complex differential geometry of algebraic varieties. So both of these questions make sense, at least in general, namely, can we construct moduli of K polystable varieties in higher dimensions that are not Fano, but come with a polarization? And can we connect K polystability to Kähler geometry? So both of these are reasonable questions. Makes sense, except we just need to include a polarization. So questions make sense for general polarized varieties. So that just means pairs XL, where X is projective and L is ample. Ample line bundle or even Q line bundle if you prefer. Okay, but actually here we know very little. The state of the art for the general case is really very far behind the Fano case. So in particular, my first claim is that we actually don't even know what the right condition generalizing the notion of K-stability for Fano varieties actually is. As in, K-stability is surely not the right condition to be related to moduli theory and Kähler geometry outside of the Fano case. Probably you need something stronger, we don't even know what that stronger thing is as such. So, I mean, we have guesses, so I'll say we're not even certain because there are even kind of competing conditions that might be the right ones to consider. So we're not even certain of the right definition. Right as in the condition that allows us to connect with moduli theory and Kähler geometry. So away from the Fano case. So by that, I mean, we surely need to strengthen case stability in some way, and it's not exactly clear exactly the right way of strengthening it. So case stability, maybe the most well-known and popular of these strengthenings is, so it's often strengthened to what's known as uniform case stability. I won't really emphasize this so much in the talk, but this is basically a stronger numerical condition. I'm not really assuming that you know what case stability is. We'll come to that maybe later. But at least this is a strengthening of case stability by kind of strengthening the numerical criterion that is involved in the definition of case stability. So this is a stronger numerical condition. Yeah, I'm ignoring the many people who've made progress in these kind of directions. I'll mention I saw Matthias in the audience, so he was one of the people involved in the story. So that's one way of strengthening case stability, but another important thing to consider is maybe generalizing the class of degenerations that you consider. So by including more test degenerations. So case stability involves basically you try to assign some degenerations or generalized degenerations. You associate a number, you ask that this number is positive. But you might consider kind of wider classes of degenerations or kind of formal generalizations of degenerations. So this is really what's happening in the non-Archimedean approach to case stability. Or older and more relevant for today, what Donaldson called arcs from about 10 or 15 years ago. Okay, so the point is that basically in general, we don't really know what the right notion of case stability is. We should strengthen it, surely. There's kind of very compelling evidence that we should strengthen it. But then when we do strengthen it, we would like to be able to actually prove stronger theorems that we weren't able to using case stability itself. So the goal for today is to basically do exactly that. So I'll give a new kind of, rather than numerical, genuinely geometric characterization of what case stability actually means, but really a stronger version of case stability. So a new geometric interpretation of a stronger version of case stability. Okay, this is uniform case stability with respect to arcs. I'll try to explain what these things are with an emphasis on the theory of arcs. Okay. And in particular, the actual applications will primarily be to Kähler geometry. I won't really emphasize these again, but they'll come in the kind of last 10 minutes of the talk. Okay, good. So in what sense do I mean that this is a geometric interpretation? I just want to advertise here. What I mean is that the interpretation, so the new geometric way of thinking about what case stability this numerical condition actually gives you, it comes through Jean-Paul's theory of what he calls stability of pairs. So this is not like, I just emphasize that this is distinct from the theory of log pairs that exists and is prominent in birational geometry. So this is a pair in a different sense that we'll come to later. Really, you should think about this as some generalization of geometric invariant theory. So this is generalization of GIT, Mumford's geometric invariant theory, which is the quotient theory of algebraic geometry. Okay, so in particular, really, again, just in case you got lost by the end of this talk, I'll advertise. Really, I mean, what we're doing is motivated by existing questions in the field, and in particular, we'll prove a conjecture of Tian around Tian's notion of what he calls CM stability. But I just want to flag here that actually, although he calls it CM stability, this is really a purely analytic condition. So this is purely analytic. Okay, and in particular, because we solved this conjecture of Tian, we'll be able to get a new proof of the Yau-Tian-Donaldson conjecture, namely the equivalence of k-stability, or this actually the stronger version of k-stability, with the existence of Kähler-Einstein metrics in the Fano case. So we get a new proof of just a version of, rather than the strongest version of, the Yau-Tian-Donaldson conjecture, namely the equivalence of Kähler-Einstein metrics existing in k-stability for Fanos. Okay, so that's where we're going in the talk. Actually, really, the talk will mostly be about this theory due to Jean-Paul of stability of pairs, which is a generalization of GIT. So in particular, I'm just going to talk a little bit about GIT, how it works, and then the generalization of stability of pairs, and how we can try to understand this theory of stability of pairs. So, okay. I'll begin with GIT. I won't assume that you know GIT already, but I won't spend a lot of time going through many of the details. So it'll be a slightly brief introduction to some of the key points of GIT. So the setting of GIT is that we have X embedded in projective space. X is projective, and I'll always work over the complex numbers, though that's not totally essential, nor is projectivity. And I'll take G acting linearly on V, so the overlying vector space, and I'll take G to be reductive. So as we're working over the complex numbers, this means that G is the complexification of a maximal compact subgroup, for example. But in the talk, the special linear group and the general linear group are the only ones that will play a role. So the goal of GIT, being the quotient theory of algebraic geometry, is that we want to construct a quotient X mod G, but we have to define what we mean by a quotient. So GIT, again, geometric invariant theory, does this, but it only parameterizes certain orbits. So, I mean, a quotient space should parameterize orbits. That would be the ideal situation. That's not possible if you want to have a separated quotient. So you need to select a nice class of orbits that you actually parameterize. So GIT only parameterizes what are called polystable orbits. So you have to kind of throw away some bad unstable orbits that are not represented in the quotient. So this is sort of the finite dimensional motivation for this whole story of k-stability. So what does polystability mean? Well, first of all, I'm going to define what semi-stability means. So we'll let my notation will be suggestive of what's to come later. So I'll take point V sitting inside X with lift. So I just take any point in the line overlying it in the vector space. So with lift V hat inside V. Then V is semi-stable by definition if the closure of the orbit of V hat doesn't contain the origin. Again, actually, there are lots of different definitions of semi-stability in GIT, and usually this is rather seen as a characterization of what semi-stability means. This one will be the most convenient in actually stating and understanding the kind of results later. So what's the first theorem, which is really the main theorem of geometric invariant theory? So there is a quotient. And of course, one should formalize what you mean by a quotient, but I'll leave that implicit. X mod G, which depends on the embedding in projective space, and whose points, so closed points, correspond to equivalence classes, not exactly of, it doesn't quite correspond to semi-stable orbits, but it corresponds to equivalence classes of semi-stable orbits. Orbits where, what do I mean by equivalent? I mean that V is equivalent to some V prime if the closures of their orbits intersect. Okay, so I'm really parameterizing equivalence classes of closed orbits. Send a theorem that actually inside this equivalence class, there's a unique closed orbit. Okay, so if we in particular define V to be polystable, although again, this is a theorem, so if G dot V hat is actually closed, if this orbit is closed, then the GIT quotient has points corresponding to these polystable orbits inside X itself. So it's polystable things that are represented in these finite dimensional quotients. GIT quotient parameterizes polystable orbits. Okay, so we get this actually very simple to define quotient. I mean, said another way, you can construct this quotient kind of algebraically by looking at proj of rings of invariant sections. But you would kind of like different characterizations of how you should understand polystability. So your quotient is only capturing the polystable orbits. You would like to understand the polystable orbits. So there's first of all an analytic characterization. I mean, I say analytic, it's actually kind of not serious analysis. But we'll just choose a norm on V. So we'll let this be a norm on V. Then we have the following lemma due to Kempfness. Okay, so this says that V is semi-stable, although there are versions for stability or polystability, if and only if the function G to R, sending G to the log of the norm of G dot V hat. Remember, V hat is the lift of V to a point in the overlying vector space. So we need this to be bounded below. I mean, this is really not a hard result, which is why I've kind of downgraded it to a lemma. The point is just like semi-stability means that the closure of the orbit contains the origin. If that's not true, there is some distance, and that tells you that the log of the norm of that thing is bounded below because the norm has a lower bound strictly greater than 0. Okay, that's a kind of analytic characterization, and we also want a numerical characterization that's maybe slightly more straightforward to work with in practice. Okay, so what do I mean by numerical? What I mean is that we'll have some kind of degenerations of our point or our orbit. We'll attach a number to that, and we'll ask that number is positive. So we'll let rho from C star to G be a one-parameter subgroup. So that acts on X by hypothesis, and I can specialize X, or my point V to some V0. So we'll let V0 be the limit as t tends to 0, rho of t dot V. Then, in particular, V0 is a fixed point of the C star action. So if I think of a point on the line in the vector space V lying above V0, then I have a C star action on that line. So we get a C star action on the line inside V, which I'll write just the span of some V0 hat, which is a one-dimensional complex vector space. In particular, the C star action has to be of the form Z goes to t to the gamma Z for some gamma an integer. Okay, and we'll define then a number, mu, called the weight. We'll set mu of rho B to be minus gamma. That's maybe slightly ahistorical, but it fits better in with case stability. So theorem C is the Hilbert-Mumford criterion, which is what makes GIT an effective theory and one that you can actually compute things with. So it says that V is semi-stable if and only if, for all one-parameter subgroups, rho, the weight is actually non-negative. So mu of rho B is greater than or equal to 0. Okay, so there are versions, again, of this for polystability that I won't really get into, but the point is that we start off with this question of how do we construct quotients. We get some abstract answer, and then we get a kind of analytic characterization, which is beneficial, and we also get a numerical characterization, which is beneficial both for kind of different reasons, but in particular, one thing maybe I'll just flag that you get is a kind of numerical characterization of when some kind of log norm functional is actually bounded below. Great. Okay. Any questions on the GIT? Okay. So yeah, I mean, everything I said just there is known from the 60s for GIT, and I guess the Kempf-Ness theorem was probably the 70s. So stability of pairs. So the main point is, okay, so GIT, it's this beautiful theory, but it doesn't work as well as it should. And in particular, when we're interested in higher dimensional problems in algebraic geometry, as the Simons collaboration grant tells us we should be, GIT very rarely applies in practice. So GIT, it works very well for theories related to curves, like constructing moduli of curves or moduli of stable vector bundles over curves. But anytime we pass to higher dimensions, the techniques of GIT basically fail. So rarely applies in higher dimensions. So when we're interested in constructing moduli spaces, for example, in higher dimensions. Okay, so this theory of stability of pairs, what it's intended to do is give a more flexible generalization that should be kind of harder but more applicable. So this theory of stability of pairs, and so this is due to Sean Paul, this gives a flexible generalization. Essentially, we would like a version of GIT that works beyond the kind of classical setting that's probably, unrealistic to expect all of the nice properties of GIT to hold more generally, especially in the context I'm talking about. But nevertheless, that's the ambition of this theory of stability of pairs. So we'll let G now act on a pair of vector spaces V and W linearly. So one imagines that GIT is the setting where we have a single vector space, and I'll explain how that works in a moment. The key definition is the following. I'll kind of give some motivation as to how you should think about this in a moment, but so a pair VW inside the projectivization, so these are square brackets, P of V direct sum W, this is semi-stable if the closure of the orbit of this point, VW, does not intersect, no longer, we don't ask for the closure of the orbit to hit 0 anymore, but rather 0 direct sum W. So projectivization of 0 direct sum W is empty. Okay. So how do we, first of all, recover GIT? So we'll let here W just be C. My point W, well, any non-zero point, but I can take W equals 1. And I give W the trivial action of my group G. Okay, then how does this work? So G dot V1 closure intersects P, or intersect P of 0 direct sum C. This is empty. What this means is just that G dot V hash closure does not contain the origin. So it's just like, you imagine like, choosing the point 1 is sort of like dehomogenization of projective varieties into affine patches. So it's sort of like a GIT version of that statement. And so in particular, this is true if and only if V is semi-stable. So we recover in this way traditional GIT. Okay, that's sort of just how this generalizes GIT. Now I want to give some motivation that should make it much clearer where these ideas come from or what the point of them is. So I'll let G act now on X and L, where X is a projective variety or projective scheme, but L is maybe not ample. And really, I'm interested in a case where L is not ample, or at least not known to be ample. So then I can at least write L as A minus B. So I'm using like additive notation for, I guess, tensor products of line bundles. But, well, yeah, anyway. So we can write it as a difference of very ample line bundles. And then we can set V to be global sections of A, W to be global sections of B. And in particular, this notion of semi-stability of pairs gives us a kind of plausible version of GIT that works without ampleness. So we get a viable notion of semi-stability I mean, it's not so clear here why this, condition of semi-stability is actually independent of choice of A and B, but that will follow from the results I'll talk about later. So we get a viable notion of semi-stability for a point, say x inside x. Imagine how this should work. A lot of the problems in algebraic geometry would be solved if we knew ampleness of some line bundle in the Hilbert scheme. So if we wanted to construct like moduli spaces of k-stable varieties in higher dimensions, what we'd like to know is the CM line bundle is ample on the Hilbert scheme. That is false. We don't have that kind of positivity, and it's just unrealistic to expect these kinds of positivity statements in higher dimensions. So nevertheless, at least we can still write something ample not ample as a difference of ample things. And this gives us some kind of way of thinking about how we should think about stability for line bundles that are not ample. So yeah, I think a lot of higher dimensional algebraic geometry, we either know some line bundle that we would like to be ample is actually not ample, even when we kind of expect it to be ample. Usually that comes as a consequence of very hard results rather than something that comes from the start of the theory. So the following lemma then gives a kind of analytic characterization of semi-stability of pairs. So VW, my pair VW is semi-stable if and only if there exists a delta greater than 0. So it's again going to be a kind of boundedness of some functional with log of the norm of g dot v hat minus the log of the norm g dot w hat is bounded below by minus delta for all g and g. So we get a kind of version of the Kempf-Ness characterization, but for a difference of log norms rather than a single one. That's kind of parallel to what I was saying here about writing L as a difference of ample line bundles. So I'll call this condition that the pair VW, the pair of points, this is analytically semi-stable. What I was saying is that some of the key results of GIT are the characterization of semi-stability analytically and then also numerically through the Hilbert-Mumford criterion. And the following example shows that actually the Hilbert-Mumford criterion must fail in general in this setting. So this is an example due to Paul, Sun, Song Sun, and Zhang, Junsheng Zhang, from just actually 23, which is now 2 years ago rather than 1 year ago. So it says that there exists G, V, and W that are completely explicit. So actually G is just SL2. V and W such that the pair VW is not semi-stable, as in unstable, but the natural definition of the weight of the pair being just the difference of the weights, this is actually always non-negative for all rho one parameter subgroup. So this is saying something kind of deep about the theory of semi-stability of pairs. So like when we lose ampleness, we should expect some things to fail. What this says is that once we lose ampleness, one thing that fails is the Hilbert-Mumford criterion. So the numerical condition fails in this generality. Criterion fails. Okay, so what can we do? I mean, of course, one could just give up here, and we shouldn't. We should do something else. So what we should do is think kind of how can we enlarge the class of test objects, test degenerations, namely C star actions, to something for which we can actually get a viable numerical criterion. So the following definition is due to Donaldson, I guess, but actually arcs, so this is the definition of an arc. I mean, the usage of arcs, I guess, goes back at least to Nash, but surely before that. So an arc is a morphism no longer from C star into G, but instead from spec rather than spec of like C of T inverse, we have spec of Laurent series into G. Again, it's not required to be a group morphism or anything. I'm not giving any kind of group structure to the objects on the left-hand side. This is an algebraic geometry seminar, so I guess people are kind of happy with what this means, but I'll just mention as well that if you prefer kind of thinking analytically, you could think about this as a holomorphic map from the punctured disk into G. And what I'm doing is just taking a formal neighborhood of the origin inside the punctured disk inside C. Spec C of T is the algebra geometric version of the punctured disk. Yeah. So in particular, these generalize one-parameter subgroups. So I've got a map from C star into G, then I can just take restrict that map to a formal neighborhood of the origin. We'll get an arc. These arcs are more general. Okay, and so I'm going to just do a little bit of kind of vaguely explicit algebraic geometry. So if I've got an arc, then I can think about what rho.v hat and rho.w hat are. So these are, kind of vectors, but vectors with entries in Laurent series. So these are vectors of Laurent series. So, v hat and w hat, they're just vectors in V. I act by my arc, like through its image in G, and what I'll get is just vectors, but where all of the entries are Laurent series in a single variable. So that allows me to extend the definition of what the weight is. So I can now say that the weight of an arc, generalizing the weight of one parameter subgroup, it's just the order of vanishing at the origin, or at zero, of these vectors, but I take the difference of them, and the sign flips as usual with these weights, plus ord 0 of rho w hat 0. Yeah, so I look at the, sorry, not 0, I guess. Good. Okay, so these are vectors of Laurent series. So I just look at, what is the order of Laurent series? It's just the kind of highest power of negative, like if it's t to the minus 5 plus higher order terms, then the order is 5. And if I've got a vector, I just take the lowest entry, like of the orders of each of the entries of the vector. So this is, again, something kind of explicit, but so we say, it allows us to give a generalization of what numerical stability means. So we'll say that VW is numerically stable, semi-stable, if this weight associated to all arcs is non-negative. Okay, so we extend from one parameter subgroups, which cannot give us a numerical criterion for stability of pairs, to including arcs, where we have a kind of upgraded version that allows more general test objects. So the first theorem then of, all of this is joint work with Rémi Reboulet, who's in Lyon. So the first result, actually not that hard, is that this pair is semi-stable if and only if the pair is numerically semi-stable. Okay, so we got a kind of numerical criterion and a kind of optimal numerical criterion for semi-stability of pairs, but where we use arcs rather than just one parameter subgroups. So we introduce, so Paul also has a notion of a stable pair, which is an upgrade of semi-stable. We also introduce a notion of a polystable pair that will be useful in stating theorems. Polystability and actually the proofs in the polystable setting are kind of harder than the semi-stable case, and prove. Sorry, question. Okay. Okay, theorem, again, of myself and Rémi. So the following are equivalent. So this is just kind of generalizing from the semi-stable case to the polystable case. So this pair VW is polystable. The pair is numerically polystable. And the pair is analytically semi-stable. So that's a condition on these difference of log norm functionals. This is analytically. Polystable. Okay, so the slogan is that if we try to do GIT without positivity, then we can't use one parameter subgroups for the Hilbert-Mumford criterion. we must do something more general. And this theorem says that arcs are the right kind of level of generality with which to work if we want to do GIT without ampleness. Okay, and the second thing I just want to say is that really the theory of polystability and kind of orbit closures is not relevant to the applications itself. Rather, in the applications, what I'll be interested in is the equivalence of 2 and 3, where this gives us a numerical criterion for boundedness of some functional. So this is where the applications come from. Okay. Sorry. Good. Okay, applications. Yeah, any questions about this kind of general theory of stability of pairs? Very happy to take a question. It's good to get questions when you're speaking online, I think especially. Okay. Okay, so how does GIT work? Just to kind of remind you, usually you apply it to the Hilbert scheme or the Quat scheme or something like that. And what the Hilbert-Mumford criterion allows you is to say that in those kind of settings, what you really need to do is consider one-parameter subgroups acting on the Hilbert scheme. What that means is you take your variety or your sheaf, depending on if you're dealing with the Hilbert scheme or the Quat scheme, you take the flat limit under the C star thing. So you degenerate your variety or your sheaf. You associate a number, that's what we've been doing, and then you ask that that number is positive. That's the way you try to apply the Hilbert-Mumford criterion. So it tells you that you should consider flat families like degenerations induced by C-star actions of your variety or your sheaf. For sheaves, it turns out that that's equivalent to giving a filtration of the sheaf, which is how subsheaves come in. But in the varieties case, it's this secondary task of trying to geometrically decipher that. So in particular, what this will say is that really what we should be doing if we lack this kind of ampleness is to try to understand more general degenerations of varieties than ones induced by one-parameter subgroups. But I'm just going to try to say, okay, so how do we actually construct a pair from a variety? So I've been, writing down pairs. I've been kind of saying some of this is fairly arbitrary, but actually there is a kind of classical 19th century way of doing constructing a pair from a variety embedded in projective space. So because I'll be interested in applications to complex geometry, so I'll let X be now smooth, projective, dimension n, L ample. Okay, and in particular, I'm going to embed X in projective space by taking global sections of some tensor power of L. And I'll write this as Pn. And in particular, this defining 2 points. So very, very classically, yeah, actually a multitude of points in projective associated vector spaces from this kind of information. But in particular, what I'll be interested in are 2 points. One of them is the Chow point, which I'll define in a moment, very briefly at least. The second one doesn't really have a canonical name. I'm going to call it the discriminant point. All of this, Jean-Paul, when he talks about this stuff, always attributes all of these ideas to Kähler in the 19th century. I've never actually read any of Kähler's work, unfortunately. I would say that one can read the book by Gelfand, Kapranov, and Zolovinsky for these kind of constructions. They attribute a lot of these ideas to Kähler as well, but I'm not sure if they're just being modest or not. Okay, so what do we do? So the set. So I'm first of all just going to define what the Chow point is. So the set, of n plus 1 hyperplane sections, h0 up to hn minus n. Inside, where does this live? The projectivization of the dual projective space. But to the n minus n plus 1, Christ. Okay, I'm going to do something very bad and zoom in and try and squeeze this in, and then you won't be able to see it. But n minus n plus 1. Okay, yes. Okay, such that x intersect h0 intersect the final one. The ones where this are not, so generically for dimension reasons, you expect that if you have one fewer than that, you always have intersection. So here I'm adding one more and I'm asking that they don't intersect. It turns out that this is actually a codimension 1 condition in the space of in the Grassmannian defining these things. This is a hypersurface in a Grassmannian. The Grassmannian has Picard rank 1. So in particular, this hypersurface is the vanishing locus of a single section of the kind of line bundle O of 1 on the Grassmannian up to some tensor power. So you get a defining section. So we get a defining section. And I'll just write it or X, which lives inside V. Okay, so this is just how you define the chow point. The point of doing this is partially so I can explain how you generalize this. So we get, if we consider instead the set H0, and now we include one fewer. So this is in P, again, the dual projective space, but to the n minus n. And here instead, what I look at, rather than asking that it vanishes, so generically this will hit X in D points. So this will be D points, and I just ask for this to be not D points, so that fewer than D points. So the literal number of points not counted with multiplicity of X intersect H0 intersect Hn minus n is not equal to D, where D is the degree of X. So D is explicitly RL to the n, so it's just the degree of X. So generically, hyperplanes will hit X in exactly D distinct points. And here I'm looking at the locus where I get fewer than D points, where you get multiplicity coming in, of course, but I ignore multiplicity in this count. So this turns out to be a codimension 1 condition. In particular, I get, from the same process, we get delta X, which is in some other vector space W. N minus n should be n equals dim X. What's the question? You mean here, this n? Yeah, so let me just say that I'm not going to get these numbers right. And I think if I try to fix these numbers, probably surely Chen-Yang is correct in any correction to the numbers. But you just do it so that it's like you do the right number of hyperplane sections, so you get a codimension 1 condition. I gave this talk a few months ago and I got this wrong, these numbers, and I thought like, okay, I'm really going to get them right this time. Anyway, wishes don't always come true. Okay, yeah, so this is the correct way of doing things up to changing the numbers a little bit. Apologies for that. Okay, so in particular then the general linear group n plus 1, this acts on V and W. So this all fits into the theory of stability of pairs. So we get a pair or X, delta X, inside of P of V direct sum W, and we can try to apply the theory of stability of pairs to this pair. This construction was kind of highlighted by Paul in his paper introducing this theory of stability of pairs. The construction is related, and I mean, okay, so I was trying to be kind of reasonably precise before. In the final 15 minutes of the talk, I'll be a little bit more vague about things. So this is related to finding, through Paul's work, it's related to finding omega in C1 of L, Kähler, with constant scalar curvature. So constant scalar curvature Kähler metrics, constant scalar curvature. So in particular, these are the right generalization of the Kähler-Einstein condition beyond the Fano-Calabi-Yau or canonically polarized case. So e.g. Kähler-Einstein. Okay. So in particular, this problem of finding constant scalar curvature metrics, which is the center of the Yau-Tian-Donaldson conjecture, this is a variational problem in the sense that we can try to attack it using variational PDE techniques. So this CSCK problem, constant scalar curvature Kähler, this is variational. What do I mean by that? Well, there is a functional, there is a so-called Mabuchi functional M from H to R, where H is now the space of Kähler metrics. This is some big infinite dimensional space. Kähler metrics inside my first term class, my ample line bundle. Okay, so I got a functional on some big infinite dimensional space, where in particular, I can understand the existence of constant scalar curvature metrics through this this functional, such that the existence of CSCK metrics is equivalent to a condition on this Mabuchi functional. So this is equivalent due to Chen and Cheng, who proved the kind of definitive result, to existence of epsilon and delta greater than or equal to 0, sorry, strictly greater than 0, such that for all Kähler metrics inside the space of Kähler metrics, we have something slightly stronger than being bounded below. It's called coercivity. And I won't tell you what this notation actually means, especially what this subscript T means, except to say that T is you have to take into account a maximal torus of automorphisms of your starting variety. So this is a maximal torus. Okay, so the point that you should take away is that the existence of CSCK metrics can be captured through a functional. And what I've been trying to emphasize earlier in the talk is that we can try to understand properties of functionals through numerical conditions. So we'll set HR, which lives inside H, to be the space of kind of the simplest possible Kähler metrics that you can find, namely just the Fubini-Studi metric defined through some embedding. So space of Fubini-Studi metrics from some embedding. So X sitting inside P of H0 of X or L. Yeah, so I should say, I mean, if you're kind of rusty on your Kähler geometry, you get a choice of Fubini-Studi metric once you choose a basis of the overlying vector space. You need to choose homogeneous coordinates to get a Fubini-Studi metric. Different choices of homogeneous coordinates will give you different metrics on projective space and hence on X. So actually the space HR, this is a finite dimensional space of Kähler metrics. Okay, so the theorem is the following. Again, joint with Rémi. Okay, first of all, XL is uniformly K polystable with respect to arcs. With respect to arcs. So I haven't actually told you what that means yet, but maybe one can imagine what it might mean by trying to apply the results that I just spoke about to the Hilbert scheme. And secondly, there exists an epsilon and a delta OR greater than 0. So delta depends on OR, such that Mabuchi functional on omega is bounded below by epsilon, and then this norm of omega minus delta, but again, delta depends on OR. So this is true for all omega induced by this embedding inside this fixed projective space, so this finite dimensional space of Fubini-Studi metrics. This condition here, this analytic condition, this is what Tian calls CM polystability, or I mean, I guess he defines CM stability, but it's the right generalization to the case of having automorphisms. This is CM polystability due to defined by Tian in 97. So yeah, I should say as well that basically this result was conjectured by Tian in this paper from 97, where he outlines this program to prove the Yau-Tian-Donaldson conjecture. And so he conjectured that this would be true. And yeah, that's been one of the goals of the field, I guess, since then. It seems that just this is extremely hard or impossible if you only use test configurations, which is really what Tian was trying to do originally. And the point is that if we include arcs, then we're able to prove this conjecture. So kind of a benefit of arcs. And just one other thing that I'll highlight is that the dependence of delta OR on OR, this is all that prevents a full solution of YTD, the Yau-Tian-Donaldson conjecture from this perspective. So all that prevents a solution of YTD, namely the equivalence of the existence of a constant scalar curvature metric with some version of K-stability, where here this would be. This version, I should say, I mean, like the independence of some constant and some other variable sounds like it might be not such a hard problem. This seems to be an extremely hard problem. So I'm not saying that this is something that kind of will imminently lead to a solution of the Yau-Tian-Donaldson conjecture or anything, but at least it is some progress in that direction. And in particular, we do know that we can take this this delta OR independent of OR in the Fano case. So this is a corollary which contains three steps. One is due to the previous theorem, another is due to Tian in his 97 paper, and another is due to Sekedi, 2016. So X minus KX Fano, so I take a Fano variety, Fano manifolds with the anti-canonical polarization. This admits, this is uniformly K polystable with respect to arcs, if and only if X minus KX admits the Kähler-Einstein metric. If and only if I can find a Kähler-Einstein metric on my Fano manifold. And yeah, this is proof number, I don't know, 7 of this conjecture or something. I mean, this gives one possible solution of the Yau-Tian-Donaldson conjecture for Fano manifolds, where we're really giving, a proof of one of 3 steps from Tian's original program. I think, we're assuming the most on the stability side. And so really the point of being interested in this is that actually this is exactly how Tian in 97 envisaged that you should prove the Yau-Tian-Donaldson conjecture. And also many of the ideas work in general, so we get results for general polarized varieties as well. But again, this is not the strongest proof, the strongest strongest statement in the direction of the Yau-Tian-Donaldson conjecture. And it's certainly not the most simple proof either. Okay, so I'll just end with some explanation of what uniform K polystability with respect to arcs actually is. But what I really want to highlight is that all of this is, a somewhat straightforward application of the theory of stability of pairs. So the proofs are applications of the results that we proved around stability of pairs. So an arc rho in GL n+1. So remember, this is acting on my projective space, P of H0 of X or L. So this gives a flat family. So you should think that, GL acts on projective space, inducing an action on the Hilbert scheme. And so we can try to apply this theory to the Hilbert scheme. In particular, this gives a flat family curly X, curly L over spec of ring of formal power series with the general fiber, the generic fiber, X or L, by taking the flat limit or taking the closure in the Hilbert scheme. So basically just apply the valuative criterion for properness to the Hilbert scheme by taking the flat limit. And we actually, I should say, because it's going to get confusing if I don't say it, you get a little bit more. You get an identification of this family with the trivial family. So like the general fiber, you get an identification from this with XL or X or L. So that's kind of important that we get something that is slightly more than just the family. We get an identification, a trivialization away from 0. Okay, so then we define a number. So the Donaldson-Pataki invariant of an arc, it's n over n+1, n is the dimension of X, and then minus kx dot L to the n minus 1, which looks like the first coefficient of the Hilbert polynomial in asymptotic Riemann-Roch over L to the n, which looks like the leading order term of the Hilbert polynomial. And then I do OR inverse L to the n+1, plus, and I'll tell you how to interpret that in a moment, OR inverse L to the n dot relative canonical class over spec C T. I mean, okay, this is just the relative canonical class anyway. Okay, except, I mean, curly X is certainly not proper. And so one needs to try to understand what you actually mean by intersection theory. And the point is that you can use the trivialization of this family away from 0, the fact that we have a trivialization away from 0, to make sense of this intersection number, even though we're not dealing with proper things. That's something that's kind of familiar from the non-Archimedean story of Buxom, Fav, and Johnson. That's one of the ways in which they define intersection numbers when they're kind of defining energies in their proof of the non-Archimedean Colbier theorem. So this is suitably interpreted. So we get a number associated to an arc, and we prove this is actually the number that comes from the theory of stability of pairs. So this, and really for the experts, I should replace this with what you might call the non-Archimedean Mabuchi functional. And we prove this is the weight rho of this arc rho with respect to the pair of points considered by Paul, namely the pair of the Chow point and the discriminant point. So we identify the weight with this Donaldson-Fataki invariant. So we have a geometrization of what this numerical criterion for stability of pairs is actually giving us. Okay, and then the point is that a result of Paul, a kind of famous important result of Paul, relates the Mabuchi functional on the space of Vini-Suri metrics to the log of the norm of G dot Chow point minus log of norm of G dot discriminant point. So we get a relationship between boundedness of this functional, non-negativity of this weight, so in particular non-negativity of this number, which is the Donaldson-Fataki invariant, for these kind of geometrization of arcs, which are flat families over spec of C of power series. So anyway, that's the sort of ingredients that are involved. That's everything I wanted to say. So I'll be very happy to take any questions, and thanks for listening.
Thank you so much for a great talk. Any questions for the speaker?
Maybe. Can I ask something? So can you prove, I assume you have tried, directly prove that uniform K stability or polystability implies this uniform arc stability?
Yeah, that's a good question. And the answer is yes, I have thought about this. I mean, it seems kind of hard, I guess. So it's basically proven by Chen Yang, actually, in his EMS survey in the Fano case. And so one should imagine kind of like what ingredients are the ones that go into that. I mean, it's based on many of the ideas in the Bloom-Zhu paper on separatedness of K moduli. Okay, so if you're given an arc, you've also got a trivial arc, and you can kind of go from the kind of trivial. So basically what you get is a sequence of test configurations specializing you to a sequence of different schemes from your arc. As in associated to an arc, you get a sequence of test configurations. You don't get a single test configuration, and so you run into these kind of finite generation issues. The way that you deal with that in the Fano case is that you use the Ding invariant rather than the Donaldson-Fataki invariant, because that has better approximation properties. So here you run into exactly the same circle of questions of how do you deal with sequences in K stability. And so, I mean, you know, the natural language for attacking those problems, I guess, is really non-Archimedean geometry. But I think that's probably the right way of phrasing the question, but it's not so clear to me that it necessarily helps you with answering the question at the moment. But yeah, so one can follow the first steps of the proof in the Fano case, but you run into these finite generation questions. So basically what you do is, like, if you've got an arc, you get a filtration of the section ring of your polarized variety, but there's no reason to expect that's finitely generated.
Okay, well, thanks.
Actually, can I ask a very naive question? So you gave this example of Paul's theory, where basically, again, you start with a variety embedded in some projective space, and then you take the Chow point and the discriminant point. But again, in this case, you can just do the classical thing for the Chow point. So how do the two notions compare?
Yeah, that's a good question, and that's a kind of deep question that was important historically in the field. So if you try to understand stability of the Chow point, then there is a numerical condition for that, because the Chow line bundle is actually ample on the Chow variety, or yeah, is ample on the Chow variety. It's then semi-ample if you consider it as line bundle on the Hilbert scheme. So that fits into classical GIT, and in particular, you can apply the genuine Hilbert-Mumford criterion to understand stability of the Chow point. In terms of that, how that compares with what I presented today, it's a deep theorem of Donaldson that if you have a constant scalar curvature metric, that implies that if you embed in sufficiently large projective spaces, then the Chow point is GIT stable. So what you would expect is that at least in sufficiently large projective spaces, stability of the pair actually implies stability of the Chow point. Now, how you prove that kind of statement directly it's really hard. It's one of the final problems in algebraic geometry that actually differential geometry seems much more well equipped to deal with. So yeah, it's a hard question, but it's been an important one in the field.
Yes, thank you. Are there other questions for Rui? Okay, if not, thanks again. That was a great talk.
Thank you.